Hey there, Stat 200. This office hour I'm going to be talking about one-way analysis of variance. We also call that ANOVA. Let me just write that out. So we call it ANOVA. And that's kind of a shortening for analysis of variance. That's where we get that. So what is ANOVA really? So it's an analysis of variance, sure, but really what it's most analogous to is kind of an extension of a hypothesis test about two means. So imagine we have a hypothesis test with two means. We have our null hypothesis is mu1 equals mu2, and our alternative hypothesis is mu1 doesn't equal mu2. Okay? Now, an ANOVA is kind of like an extension, except now we have more than two groups. We have 3 or 4, etc. And we rewrite this hypothesis right here, these hypotheses for the hypothesis test, to instead say, let's say we have 4 groups. So now this becomes a null hypothesis of mu1 equals mu2 equals mu3 equals mu4. Ran out of space there, but you get the point. We're just extending that null hypothesis. Now the alternative hypothesis is a little bit different, and you can't actually represent it in a nice, easy mathematical notation like this right here. What you have to do is you have to kind of write it out. You have to say, not all groups have the same average. So the reason I have to write this out is if I wrote mu1 is not equal to mu2 is not equal to mu3 is not equal to mu4, that's one way that not all groups can have the same average. But what if mu1 is different from mu2, mu3, and mu4, but these three are all the same? That also we would also reject the null hypothesis in that case. So we need to include all possibilities such that not all groups have the same average. So, you know, these two could have the same average and these two could have the same average, but these pairs have different averages. That's also an alternative hypothesis. That would be something we would reject the null for. Do you get my point? Any kind of configuration where they're not all equal is the alternative hypothesis. Okay? That's the key difference. And there's a lot of theory behind how this works, and that's kind of more for a higher level class. What we're going to talk about in this one is mainly the output, which is this guy right here. It's why I put this question in. And maybe just a few other things, kind of like housekeeping, or not housekeeping, but just technical things that you're going to have to keep an eye out for. Okay, so let's get started with some of these questions. All right, so I have this I have this output from Minitab Express, and the question states, on a survey conducted at a university, students were asked how they felt about their weight, and they were given 3 categories: about right, overweight, or underweight. And were also asked to record their grade point average, GPA. There were 235 responses, with 160 saying that their weight was about right, 50 said they were overweight, and 17 underweight. The question of interest is whether mean GPA is the same or differs for different weight attitude populations. Output for the study is given above. What is the mean squared error in the study? Right. So one thing I do want to hit on really quickly when we do an analysis of variance is the response is GPA, and the response in analysis of variance always needs to be quantitative. Right? It's not going to be categorical. However, the explanation, the explanatory variable, should be categorical. You see how we have 3 here? About right, overweight, and underweight. Those are our 3 categories. So remember, quantitative response, categorical, explanatory variable. Okay? All right, let's move on. So here's our output. I've written over some of it, but that's okay. Now the super important stuff is over here. And we're looking for the mean squared error. Now there's a lot that goes into this table, and maybe I'll explain some of it right now. So when we do an analysis of variance, we have something called degrees of freedom. Now it's tough to really say what is meant by degrees of freedom, but one way you can think about it is it's the weight that your treatment has. In this case, this is your treatment, right? Weight, feel is that variable. So it's our treatment. Our treatment has a weight of 2. Now you'll notice that there are 3 possible categories. The degrees of freedom are 2. So the degrees of freedom for a treatment is going to be the number of categories minus 1. That's really the most important thing for you to think about here. The total degrees of freedom, which is kind of like the total weight of the analysis of variance, is going to be the sample size minus 1, right? So there were 235 responses. The total degrees of freedom is going to be 234. And therefore, the degrees of freedom for the error is 232. The degrees of freedom for the treatment and the degrees of freedom for the error have to sum to the total degrees of freedom right here. Now what is this? Sum squared. This is what we call the sum of squares for the treatment right here, and this is what we call the sum of squares for the average. Now these are kind of trickier concepts, but really quickly, what the sum of squares for the treatment would be, so we'll call that SST. And again, a lot of this is really more technical than you're going to need to know. I'm just going over it very quickly. The SST is the sum of, so I'm going to use capital sigma here, that's the standard scientific notation to denote a sum. So that's the sum of all of the x bar I minus the total mean squared. So what is this? This x bar I, that is the sample mean for the ith group. So we have the mean GPA for the people who are about right. So we have that mean GPA minus the total GPA of the whole sample. And then we're going to square that. And then we're going to add the difference between the sample mean of people who feel overweight minus the total mean. Square that. And then we're adding those two together. And then we're also going to add in the sample mean of people who thought they were overweight, the sample mean GPA, minus the total GPA average. We're going to square that. And we add those three together, and that gives us 2.134. That's where that value comes from. Now what the sum of squares total, or I'm sorry, the sum of squares error, so the SSE, it's again a sum, so I'm using capital sigma here. But now it's not going to be x bar I, it's just going to be xi minus x bar squared. And what that is we're not going to pay attention at all to group. We're just going to take each person's GPA and subtract it from the average GPA and then square it. And we're going to add up that for all 235 people. We're going to add that up for all 235 people. And that's how we're going to get this value. Okay? So that's where we are. Now, the mean squared treatment, we can call this the MST if you'd like, that is just the sum of squares for the treatment divided by the degrees of freedom of the treatment. So if I took 2.134 divided by 2, I would get this guy. Similarly, the sum of squares error divided by the degrees of freedom for the error gives us this. That is what we call the mean squared error. The MS error, mean squared error. So this is just dividing 49.719 by 232. And you'll notice that the mean squared error here is very low. And then for various reasons, the distribution we're using here, so normally we use the normal distribution, pun not intended. Typically we use the normal distribution to conduct our hypothesis tests, but in this case we can't do that for various reasons that are outside the scope of this course. But this value, f, is another test statistic. It's similar to z, but it follows a very differently shaped distribution. The distribution for f looks a little bit crazier. It looks kind of like that. But that's a rough sketch. Don't worry about it. But this value comes from taking the mean squared treatment and dividing by the mean squared error. So if I divide 1.067 by 0.214, I get 4.98. And then from that, this we can apply to this distribution here, just like we do with the z-score, and we can find a p-value. Now this p-value is actually very similar to the p-value we've been using all along. It has the same interpretation, so in that way it's great, because we can apply that to something else. And remember, this p-value is, once again, just because this is important, the p-value is the chance of observing the data that we observed, or data more extreme, given that the null hypothesis is true. Remember, the null hypothesis is that all the means are equal, like this. Okay, so that was a very long crash course on what the analysis of variance is. So now I've already answered this question. The mean squared error in this table comes from the mean squared column in the error row, right here. So 0.214 is the answer. Okay, let's move on. A study compared grade point averages among students in 4 different majors: English, history, science, statistics, and art, using analysis of variance. A total sample size of 20 students, 5 in each major, was studied. The p-value for the f-test is 0.013. If the significance level alpha is 0.05, what's the conclusion for the analysis of variance? Now, like I said, the p-value and the significance level, those all basically have the same interpretation. So if we recall, if our p-value is less than our alpha, our significance level, then significant. Which is the same as saying reject null. Box around that, make sure we don't get confused. However, if the p-value is greater, or you could say greater than or equal to, it's very rare that a p-value is exactly equal to a significance level. Extremely, extremely, extremely unlikely. Basically impossible. But don't worry about that. We can include that less than or equal, or greater than or equal to here. Then this is not significant. Alright, not significant, which means fail to reject the null. So there's a summary of how the p-value and the significance level work together. We should already have seen this, so this shouldn't be anything new, but just to summarize. So when we go through here, we see that the p-value is less than the alpha level. We're right here, so we're going to reject the null. So that means we can already stop paying attention to this one, this one, this one, and this one, because we're not going to be rejecting it. Now, you'll notice that these two have the word population means, and these two have the word sample means. Whenever we do a hypothesis test, are we trying to make a statement about the sample or the hypothesis? I hope at this point it becomes kind of reflex. We're always trying to make inference about the hypothesis. Remember, inference is saying, well, this is what I saw in the sample, and so from that, I'm inferring this conclusion about the hypothesis. So we should be talking only about population means. So these guys, write out. We're down to these 2 options up here. And this says the population means are not significantly different, or they are significantly different. So, oh, goodness me. I actually made a mistake here. Sorry about that. I started off by saying these are not rejected. That's not true. I got a little carried away. The p-value here is less than alpha, right? So, that is significant. We reject it all. Sorry, the opposite of what I said at the beginning is what we should go with. So null hypothesis will be rejected. So one of these 4. So get rid of these, get rid of these. But the same thing holds about the sample means and the population means. We're only going to be talking about population means. So we're in here, in these two. And are they significantly different or not? Again, they're significantly different. Right? That's what that means. This is just another way of saying, okay, p-value is less than that alpha level, so it's significant, we're going to reject the null. Right? So then here is our answer. Sorry about that mistake. I hope it didn't confuse anybody there. Just misspoke. Alright. Let me know if you have any questions on that one. Next. A study compared grade point averages for students in a class. Students were divided by 6 locations where they usually sat during lecture. So we have left to right front, left to right center, left to right rear. So something like this. Right? Left and right front, left and right center, left and right rear. Total sample size of 12 students was studied. That's pretty small. So there's only 2 students in each section. 2, 2, 2, 2, 2, 2. Alright, using a one-way analysis of variance, the error sum of squares is SS error equals 50. So SSE equals 50. What's the mean squared error? So remember, the mean squared error is the sum of squared error divided by the degrees of freedom for the error term. That's what we were talking about before. And when we were talking about degrees of freedom, so we already have this value. So what we need to determine is this value right here. So what I said was we have degrees of freedom for treatment, for error, and for total. So the treatment degrees of freedom is the number of categories minus 1. So how many categories do I have here? I have 6, right? Left front, left center, left rear, right rear. 6. So therefore, the degrees of freedom for the treatment is going to be 6 minus 1, or 5. Now the total degrees of freedom, as I said before, is the sample size minus 1. What's our sample size? 12. So the total sample size, or the total degrees of freedom, is 11. To find the degrees of freedom for error, what do? I take the difference. 11 minus 5 yields 6. And from there, what we need to do is we just say, okay, well then, the mean squared error is 50 divided by 6. And if you plug that into a calculator, you find it's equal to that. 8.33. Does that make sense? That's actually, this question was what I had in mind when I started going into the analysis of variance table a little more in depth before. So it is important to get the good framework understanding down for problems like this, which could come up on the quiz. Alright. A student wanted to test whether there was a difference in the mean daily hours of study for students living in 4 different dormitories. She selected a random sample of 50 students from each of the 4 dormitories. What is the alternative hypothesis for this situation? Alright, so the alternative hypothesis, remember, is just that not all of the means are equal. That's the generic alternative hypothesis for an ANOVA, right? And we know that this is an ANOVA. It doesn't explicitly say it, but it's an ANOVA because this guy is quantitative, and we have 4 different dormitories. That's our categorical explanatory variable. So great, that fits the conditions for an ANOVA, and what we're going to do is just say, okay, remember how the alternatives that they're not all equal? So the mean daily hours of study is 3 hours for each dormitory? No. Right? That would, A, that means that they're all equal, and B, this is assigning a value. We don't do that in an ANOVA. For an ANOVA, they're either all equal or they're not all equal. The mean daily hours of study is the same for each dormitory? Again, no. That's the null hypothesis. Mean daily hours of study is different for each of the 200 students in the sample? No, we're not making a student level judgment, right? This is making a student level or a judgment on each of the 200 students. We're not doing that. So therefore, by process of elimination, and also because this matches our definition, the answer is that the mean daily hours of study is not the same for all 4 dormitories. That's what we're looking for. A study compared grade point averages, GPA, for students in a class. Students were divided by 6 locations. This is just like before. Total sample size 12 students, 2 students in each section. And now, this time, we're given a p-value right here and a significance level right here. What's the conclusion? Well, let's think. Is the p-value greater than or less than alpha? P-value, alpha, which one's bigger? P-value is, right? 0.46 is bigger than 0.05, so p-value is greater, therefore it's not significant, right? And we fail to reject the null hypothesis. So I'm sure you have this down by now. We've already harped on it enough. So let's go to the answers here. So the null hypothesis is not rejected, right? That's what I just said. So we're going to get rid of these 4 answer options. We notice we have the same thing here. We have population means for these 2 options and sample means for these 2 options. Again, please remember that all these hypotheses, whenever we do a hypothesis test, it's always about populations. So we're going to get rid of these guys. Now we're only looking at these 2. So, are they different or not? It's the null hypothesis, right? Null hypothesis, nothing interesting is going on. All the means are equal. Therefore, it's got to be this one. All right? Not rejected. We cannot say the population means are different. That's exactly what that means. Okay? So there you have it. There's our basic rundown on ANOVA. It's usually a little more intuitive at this point if you've already kind of got a good understanding of the difference in means lesson. But if you have any questions, please feel free to give me an email or give me a call. All right. Good luck on the quiz this week.